to introduce Professor Ryszard Michalski from George Mason University. He has a long and distinguished career in the field of machine learning, and in fact I thought I'd do the introduction, and so I printed out his bio sketch on 9-point font. It's a page, and if I started doing this, this would be the seminar and you would never hear from him. So I'll make a very, very truncated bio. I'll make a very short introduction. He's the Planning Research Corporation Chair Professor of Computational Science and the Director of the Machine Learning and Inference Lab at George Mason. He's had like I said, a long distinguished career, starting in Poland and continuing in the United States. He came to Illinois, University of Illinois in 1970, and he was first a research professor, then a tenured professor of computer science there until I think 87. And then he came to George Mason with his lab. He is well known for being one of the founders of the field of machine learning, and I can reel off a list of things which are credited to his innovation, or he started these ideas, things like conceptual clustering, constructive induction, variable valued logic, natural induction, variable precision logic, ... until inductive databases and knowledge scouts. And to give you some flavor of what he's going to talk about, this is his current thinking and his current ideas. When I wrote to him, I said, talk about anything that excites you. And he's decided he'd talk about knowledge scouts, and that's what we hear from him.
Thank you for a very kind introduction. Good afternoon. I had the pleasure to speak with many of you today, and I realized that your interests are in some sense complementary to my interest. You are interested, or many of you are interested in natural language processing, speech processing, image processing and understanding, while I am more interested in building systems that take natural input like language or speech and produce also natural output like natural language sentences or images representing knowledge that system has created by observing some facts or getting some data from outside. To motivate this talk, let me observe that the world produces about 2 exabytes of information a year. It is about 1 million terabytes a year, out of which only a small portion is actually used access. We clearly are facing an information overload. So today I will describe some work that we are doing at George Mason in my laboratory to address this problem of information overload by building what we call inductive databases. So my talk will be about inductive databases and knowledge scouts. I will briefly talk about the difference between data mining, which you all know about, I'm pretty sure, and what I call knowledge mining. Then we'll introduce to you this concept of inductive database. Then we'll tell briefly about a system that is a realization of our first ideas about an inductive database. And then we'll give you an example of a medical knowledge scout which lives in an inductive database. And then, if time permits, I will give you a demo of natural induction. By natural induction, we mean systems that, given some data as the input, will create hypotheses in natural form, like, for example, in natural language. So they will actually speak to you what they learned. All right. We are living in the world in which we have many, many databases now about all kinds of human activities, and also we have internet. And the presence of these technologies has created extraordinary opportunities for monitoring, analyzing, predicting processes in many areas of human activities such as economy, medicine, agriculture, science, defense, and so on. the current data mining methodologies are not sufficient for such tasks. Because we need methods that are capable of what I call knowledge mining, that can approximately be described as a process of deriving goal-oriented knowledge, so they understand what given user may want to know, and are employing advanced methods of inference and prior knowledge, so they also can reach out and analyze and involve in analyzing data the prior knowledge. We all agree that if you, let's say, you have no information, no knowledge, let's say, about the concept of President of the United States, about the United States, and so on, and started to read Washington Post, and then read about Bush President, you would not get much information from it if you don't have all this background knowledge. So ultimately, systems that derive knowledge from data must be able to derive knowledge from other knowledge, and actually from a combination of knowledge and data, and should be able to conduct in advanced reasoning involving both. And we believe that the development of effective methods and systems for what I call knowledge mining is becoming a central challenge for research on the agenda for this century. It's an enormous problem because we are facing so much information which is being generated everywhere, but our brain, at least mine, is not growing. Speed is not improving. So we have to somehow build intelligent systems that will help us to translate, to derive from the available variety of data useful knowledge, useful at any given step of our decision making. In order to justify this concept of inductive database, let me remind you about the evolution of the database technologies. Initially we had conventional databases, and we still have them. They basically give you answer if the answer is stored in the database. The so-called deductive databases then can, in addition, to derive some deductive inferences from the facts stored in the database. Now, data mining and knowledge discovery are tools, methods, systems that are sort of aside. They are not integrated with the whole database. So we have SQL as language for getting data and changing data in the database, and then we have tools for data mining. And those tools are usually quite simple. They cannot do much for us. And a natural next step is to build what we call inductive databases. Databases that are able to answer not only queries about facts that are actually stored in the databases or in a given database, but also create hypotheses and give you plausible conclusions. Like people, when you ask somebody a question and he or she may not know the answer, but may start reasoning about the answer. Like, for example, I may ask you, how many piano tuners live in Baltimore? My feeling is that none of you know exactly how many of them live here. But when you start thinking about it, you will give me some meaningful answer. You know it's not 0 for sure, and not million for sure. And you will start thinking, and you may come with some approximation. So this is what is needed. Databases that are equipped with certain capabilities for plausible reasoning. So that's what inductive database is about. But has all those capabilities integrated. Traditional current approach to data mining or knowledge discovery is that we have data, we select some target data, then we pre-process the data, then we transform the data, and then we do the stuff that is often called data mining step, and then we test the knowledge, which is usually in the form of relatively simple patterns. And then if that knowledge is tested and works well, then we store it and possibly use it for some decision making. So you can see what we are doing here from data to knowledge. There's no prior knowledge involved here. Prior knowledge is only inserted by the user or by the designer in some forms, like that designer may select attributes that are relevant. Here are the popular techniques. But these are, I presume, are familiar to you, so I'm just mentioning them. Decision trees, rule induction, neural networks, nearest neighbors, original computation, clustering techniques, Bayesian belief networks. These are currently widely used techniques. Notice that all of them do not assume some large amount of prior knowledge. They do some transformations. They start with some data and then end up with some form of knowledge, which is they are able to represent. So, strengths and weaknesses, well, simple to implement, easy to use, efficient to apply, can scale up. However, they are able to find only very simple patterns, like decision tree, let's say, or some patterns that neural network can represent. They are not integrated with the database. Unable to employ sophisticated domain knowledge, including inability to represent abstract goals that system should pursue. And knowledge generated may be difficult to interpret. For example, a neural net. Neural net may learn certain transformation, certain classification, may do it very well, but will not tell you how it does, why it classifies certain objects this way or that way. So, if application requires some explanation and understanding, this is not a good technique for such an application. Let me give you a motivational example, a real-world example. You can read. There was a case that US trade records show that in the early 80s, the import of trucks from Japan sharply declined, while the import of auto parts significantly increased. The significance of these facts was only noticed several years later when it was determined that Japanese companies were assembling trucks in the US to avoid a high US tariff on imported trucks. See, this discovery led to a new trade agreement between the US and Japan, but a few years later, so of course an amount of money was lost. Question: how could we build a system that would automatically discover such a pattern? Can we build it? How could we do it? Well, we would have to have a system that would be able to conduct inductive reasoning, create hypotheses with abstract concepts, goals, to represent and reason with background domain knowledge, and have an access to relevant facts, of course. And building such a system requires an integration of several technologies. Of course, databases, which store the facts, what's going on about those parts being imported and tracks being imported and so on. Knowledge bases that store various generalizations, patterns that are being discovered, and also prior knowledge. And advanced methods of inductive reasoning. So, what are the recent challenges now? Well, we need systems or methods for effectively, efficiently using both data and background knowledge in order to derive new knowledge. And reasoning with more advanced knowledge representations. Since data may be insufficiently relevant to the task, there is need for what we call constructive induction. That is, transformation of the representation space to a new representation space in which solution is easier to find, or hypothesis is easier to define or discover. We also need what we call natural induction, namely we would like to have output from such a system in natural form, so in the form of image, graphics, or natural language, the kind of forms of knowledge that we are used to. Not sort of some strange set of, let's say, networks which don't tell us much. So that natural induction is really important for some applications where we really want to understand what machine is producing for us. Now, the process of knowledge discovery needs to be more automated. It turns out that if you use current data mining tools, you have to use them again and again with different parameters, try this, try that, try another tool, a lot of work. Well, could we automate this process? Can we design a system that can conduct experiments automatically? Just by giving abstract goal characterizing the kind of knowledge that we are interested in, and the rest is done by the system. And such a system is called knowledge scout. So knowledge mining is an idea that talks about deriving knowledge from data that satisfies three conditions. First of all, it's guided by goals, knowledge needs of a user, that can be defined abstractly, because if we want to discover something new, we cannot define it. So we have to be able to only generally or abstractly define what kind of knowledge may be of interest to us, but systems should actually find more specific knowledge that is really interesting. We may say, well, we would like to discover things, let's say, that cause cancer of the prostate cancer in men. Find the reasons by searching all the publications on the subject and all the databases that were collected on the, let's say, lifestyles of men and then their diseases. And from all this data, find the causes, potential causes. It strives to generate knowledge in natural forms. This is what I said earlier. We would like to have that system really communicate with us in natural language or in terms of images, both having them as input and as output. And then involves a significant amount of prior knowledge. We simply know that you cannot learn much from data if you don't have enough knowledge about the given subject. So what is an inductive database? Inductive database is simply a way to accomplish knowledge mining. So it closely integrates database with methods for inductive inference, hypothesis testing, and knowledge base. So here are various requirements. Integrates diverse learning and discovery methods into a unified knowledge mining and maintenance environment, methods that can be invoked automatically according to scripts, which are called knowledge scouts, defining a high-level knowledge generation language. Employs general and domain-specific background knowledge in the process of knowledge mining. Generates knowledge in forms understandable and easy to interpret. By employing a logic-style language in visualization, can test the generated knowledge and hypothesis and use for supporting decision-making processes. So these are the criteria for an inductive database. Now there is another definition of inductive database, independently of the work we've been doing. There is a group in Finland who proposed that kind of concept, inductive database. It is storing simultaneously facts and various inductive generalizations from these facts. The problem is that from a given fact, you can derive very, very many generalizations. If you don't know what kind of generalization is of interest to you, you may overload the system, have too many generalizations to store. So our approach is to store the facts and have tools that can efficiently create generalizations and inductive hypotheses accordingly to the goal of a given user. Different users will get different knowledge generated from the same data. So that's kind of an obvious schema for an inductive database. We may have different databases. Ultimately, what we would like to achieve, hopefully during my lifetime, at least some approximation, that this may be an image database, this may be textual database, that this could be numerical database, some symbolic database. So we have different sources of data, and then the system is conducting inferences using knowledge from the base data, from knowledge base, and creating different knowledge according to different scouts. Different scouts who, as I say, live in the inductive database can produce different kind of knowledge depending what we are interested. If you are, let's say, hospital administrator, you may be interested in kind of patients who will pay bills and other related topics. But if you are a research doctor, you may want to know about relationships between lifestyle, symptoms, and diseases. Very different knowledge you are looking for. So now what we are doing is that in this process, actually that line could enter different places, but primarily here, this knowledge generation process, we have to take domain knowledge, we will do some form of natural induction, and we'll have knowledge generation language that allows us to define all kinds of operators, assemble a script, and let the system now do the work for you. So this is an example of inductive database that we designed called inlen. So we call it BAG. So we have database, knowledge base, and here are different operators. You see, those operators, they are connected to the database. So these are the standard database operators, like provided by SQL. Here are the operators that only deal with knowledge base. So knowledge base may contain rule representations, hierarchies, certain relationships, associations, statistical, let's say, relationships and correlations, distributions, and then you may want to access it, modify, change it, and so on. And then there are operators that are related, linked to this big triangle, rectangle. So these are operators that simultaneously work on data and knowledge, and as a result create new data and knowledge. Such combinations of data and knowledge we call knowledge segments. So those operators work on knowledge segments. So they can generate rules, generate trees, generate equations for the data. They do transformations, optimizations. They can generate hierarchies, conceptual clusters. They can test or apply knowledge. They can generate representative examples. They can generate representative and most relevant attributes. They can analyze the knowledge in certain ways. They can visualize by invoking various visualization programs, and they can also do statistics. Analyze would be statistical analysis. Now, to explain what I mean by induction, let me show you that what I call a fundamental equation of inference. That if you have some P, which is a set of certain statements called premises, then you have some background knowledge, which is also a set of certain statements in some language. And then you have a set of statements C, which we call conclusion. And if the relationship between those three components is such that union of those statements entail logically C. So if you have P and BK and you derive through the rules of deductive inference C, you are doing deduction. If you have C and background knowledge and you create plausible hypothesis that together with background knowledge entail C, then you are doing induction. And then you can also do analogy. If P prime is similar to P, hypothesis C prime, which is similar to C. So induction is simply reasoning in some sense backward. I mean, giving facts, giving some data which are consequent of some processes, and they logically, implied by background knowledge in some unknown premises, find those premises, hypothesize those premises. So this way, both inductive generalization, inductive specialization, abduction are forms of generally described induction. Now, natural induction. In order to conduct natural induction, namely to build systems that can create hypotheses and express them in a language that people can easily understand, we need to enrich the language in our systems conducting inductive inference. For example, we know that the decision trees are widely used in machine learning, but they are very limited knowledge representations. They cannot represent many things. You want to represent straight line using the deduction. I mean, a decision tree, you will see that you will have a very complex, bushy decision tree. In order to be able to represent simply concept that people can represent simply, you simply have to have a richer language, language which is sort of approaching natural language. However, you want to do formal reasoning, so you have to have language which has well-defined syntax and semantics. So we are looking for languages that are richer but still well-defined. So attributional calculus, a language that we are now using, is sort of a method and a language, method of reasoning and a language that satisfies those goals. It's a combination of propositional logic, predicate logic, and many-valued logic. But it has the features that it's very easy to translate expressions of attributional calculus to natural language. And you will see it demonstrated. It allows such forms like color is red or blue or green. So you can use OR, a connective OR, connecting not predicates or statements that have true or false truth value, but also atoms. That's not done in formal logic. But in natural language, of course, we do that. We say John and Mary went to a movie. John is not a predicate. John is an atom. So that's possible in attributional calculus. We can say X in some range. x equals x2, x1 equals x2, x1 and x3 greater than x5. So we are able to represent this information also in other languages, but in a much more complicated way. And this way is very much close to natural language. It's very easy to translate every of those sentences to natural language almost directly. This is an interesting concept. That's kind of an addition to the logic system that brings logic a little bit closer to arithmetic. Namely, this is a counting attribute. It says that number of variables in this set, x1, x2, x4, x6, x7, there are two variables in that set, and only two, such that their value, no, I'm sorry, other way around, that there are three or more variables in this set, any three or more, such that their value is 2. Notice that if you want to express this as a propositional calculus expression, you will use very long expression. But this is very short and actually easy to translate to English, and turns out it's very useful. For example, it's useful in medicine. Very often doctors say, well, if a patient has certain number of symptoms from that set, let's say 6 or more symptoms, then that disease holds, or is likely to be the case. So I know it because I work with doctors, and they told me that they reason sometimes like this. So that method enables us to directly represent such concepts and combine them with other concepts. So the system can say things like if x1 is smaller than x2 and x3 not equal to x4 and x3 is red or blue, then decision is A. This is a statement in natural language. That's how we would write probably in our publication. But notice that if variable xi is just for value, then representing that simple rule would require a decision tree with 810 leaves and 190 nodes, or 600 conventional rules. Conventional rules are rules that have attribute value type of conditions. Huge set of rules or large tree which would be very difficult to understand, interpret. While this statement is very simple to interpret. So in natural language it's easy to understand, but in representations that are currently widely used in machine learning, namely decision trees and conventional rules, would be very hard to represent. Very complex representation. And moreover, because of the inadequacy of the language, probably decision tree which was inferred from the data, assuming that it was only a sample of data, probably would be wrong. Because if the language is wrong, it's hard to learn right hypothesis. So in attributional calculus, we would write exactly this. This is what system would produce. Decision is equal A if x1 smaller or equal x2, and so on. It's very close to natural language, you see. And moreover, system, in order to give us more information, would annotate this statement. It would add some additional numbers, like for example, it would say that this relationship by itself holds 3,899 times in the data, in the given class which we are characterizing, and 266 times in the data or a class we are not trying to characterize, in so-called negative examples. And there would cover all, and the whole rule would cover 750 examples, and 700 uniquely. That is, there's no other rule that covers those examples. Would also would say that this is approximate rule because it covers some cases which are negative, so some exceptions. Would also have F. F is another concept. It's a concept of flexibly covered. That is, rule can be logically matching a given fact or can match approximately. To give you an example, and the idea that came from, it was when I worked in the area of agriculture. And the problem was that certain diseases occur in the summer. And all examples happen to be in the summer, let's say between June and August 31st. Imagine the situation that the disease was found on September 1st. So now clearly rule is not satisfied if it says between, let's say, June 1st and August 31st. But intuitively we feel, well, what a big deal, just one day later, so that's not really doesn't really matter. So therefore we need to flexibly match logical expressions. And that's why attributional calculus allows to multiple valued logic evaluations. All right, there's Q, some measure of quality of this rule. So the algorithm that we are using here stems from the algorithm AQ that goes back to my PhD thesis, and we're still using the core of it. And the simplest form of that algorithm is very easy to understand. It pioneered the so-called progressive covering approach, which is now used in machine learning as a term. Also, they call it separate and conquer, if you know that terminology. So you have positive examples, negative examples of some concept, and LEF is some form of criterion for judging hypotheses. And that criterion may consist of many small sub-criteria or elementary criteria, because you want to judge hypotheses from many different viewpoints. For example, is it simple? Is it accurate, or how well it performs? And also, does it have certain attributes that you want to have it, and so on. So you can define various criteria, and all together they are used through LEF to evaluate hypotheses. You select C, that is some example that is focus of attention from pause, and then you generate the star. That's the most difficult and important concept. Star is a set of different ways you can generalize a given example. Usually different example may be generalized many different ways, but consistent with the facts. So consistency is the limitation of generalization. And then you select the best rule or best generalization according to LEF from that star. And then you remove examples that are covered, and you check whether examples to be covered, POS, that set is empty. If it's empty, you already finished. You have the complete cover. If not empty, you continue that process. The more advanced forms of algorithm, they use all kinds of additional techniques. They may use methods that only create approximate hypotheses, are not necessarily complete or consistent with regard to the data. They may use various forms of elementary criteria that are being used, and a number of other variations and additional ideas were added to the algorithms that we are doing now. Right now we are implementing AQ20, so it's 20 sort of stage in this long development. But it's a lot of fun. My students love this, so I always get some students who are trying to do something new and so on. The only thing is that students don't necessarily like to finish things and produce a product that somebody else could use as a product, that have everything is well finished, well debugged, and it's a nice documentation. But however, we already have some implementations that are pretty good, so if anybody is interested in trying, we could give you such a program, like AQ19. And AQ20 is about to be finished. Knowledge scouts. So knowledge scouts utilize resources of inductive database to create personal knowledge agents that synthesize knowledge of interest to a particular user. So they live, as I mentioned, in an inductive database. They continuously and autonomously search for knowledge of interest in database. They can reduce, knowledge scout may reduce to a normal query, like SQL query, if you want to have answer online. But knowledge scout can be defined in terms of many high-level operators, can be launched, and then can live in the knowledge base in the database for weeks, and eventually find the right or approximately right answer, and will say, aha, I have something for you. And in order to build knowledge scouts, you have to have that knowledge generation language, KGL. And how much time do I have? 20 minutes? Because I would like to have 10 minutes for the demo. I think demo will entertain you. This is end of the day, so you'll have some fun. So I'll try to speed up. I prepared more material than I knew I would need, because I wanted to know what I have to tell depending on the audience. So these are the kind of things that may be a little bit not that interesting. These are kind of sort of details about how that system is working, building those knowledge scouts from the operators that I implemented as part of this. So I just skip this. So we have that language KGL already implemented. First version is implemented in this inline system. And one of the ideas is that you can apply, let's say, operator that selects most relevant attributes. So result of that would be a new table, a relational table with data that has only the relevant attributes and the facts in terms of those attributes. Then the table is submitted to a learning program. Learning program may produce some rules. Then evaluator of the rules may say, I don't like those rules. They are not doing very well on my testing data. They are too long, too many of them. So system will say, okay, now we have to make some changes in the parameters of the program and run again. So Knowledge Scout actually does such things. Evaluates, changes parameters, runs again, evaluates again, and so on and so on. So this has kind of specification of KGL that basically satisfy conditions that we need to have in order to have useful language. So now this may be more interesting. This was one of the applications of this Knowledge Scout idea using inductive database inland. The target included 75,000 survey reports selected from a database collected by the American Cancer Society. And data describe white males, non-smokers aged 50 to 65 in terms of 35 attributes, mainly relating or describing, let's say, lifestyle of this person, this patient, and some other properties like this rotundity, that is how round that person is in relation to his height. And there are 25 diseases that we consider: stroke, kidney stones, high blood pressure, gallstones, bladder disease, and others. And lifestyle attributes involve things like nightly sleep, mouthwash use, level of exercise, and so on, and rotundity, which I mentioned. So here is this Knowledge Scout definition. This is a script in KGL that defines a Knowledge Scout, which simply requests to create rules that are strong rules relating lifestyles to different diseases. So we want to find, are there any strong relationships between lifestyle of a man and diseases that we know that person has. So you can go through that script, but that's maybe too detailed. There is a publication on this matter if you happen to be interested in details of this work. And here is an example of a learned rule. So the rule says arthritis is present if high blood pressure is present, and there are 400 cases of that, and education is relatively, well, college graduate or below. So now we can start asking a question, why arthritis? Well, maybe people who are not highly educated tend to work more with their hands than with their brains, perhaps, and therefore they get arthritis easier. That now is additional explanation, but that's a pattern that we found. And then alternative pattern was stomach ulcer. If someone has stomach ulcer, there was association with arthritis too. And education, also relatively low education, and there's relatively low, none or medium exercise. Age, well, age was a very wide range. And diabetes, no, people who had diabetes somehow were not represented in those groups that had arthritis. And high blood pressure, no, you can have low blood pressure. Okay, so this is a kind of pattern which was found by the system. This is another pattern. This is an example of the data. So like data was given to the system in this form, rotundity, so low. That this person is relatively lean. Exercise, medium. Sleep, 6 hours. Education, college grad. Years in the neighborhood, that is number of years that person lived in the same neighborhood without changing. Mouthwash, yes, this uses mouthwash. And tuberculosis, high blood pressure, and then arthritis, yes, no, and so on. And there was a lot of such records. And so those records, system created this rule that I showed you. Now we can go to another topic, namely representation. So one level of representation are those rules, attributional rules that I mentioned to you and I showed you. More abstract representation is using those concept association graphs. So the concept association graphs has nodes, which in this case here are related to characteristics of a patient, like rotundity, education, But notice here we are not talking about high education or low education, because this representation is a higher level of abstraction. Now arthritis in this case is the dependent of variable. Now you see certain links, and those links have different thickness. So the thickness is greater, that means stronger relationship between like high blood pressure and arthritis. Now the condition which requires arthritis is actually composed of 4 conditions. You have to have all 4 conditions that to have strong case of arthritis. And the most important is high blood pressure, and it is positively related. Plus means positively related. That is, higher blood pressure, more likely you will get arthritis. And here rotundity also plus. If you are rounder, more likely to have arthritis. Education was minus, so it was other way around. You have lower education, more likely you have arthritis. Now, so this is, you see, that representation gives us immediately certain feeling what's going on, what things are related. And if you want to know more precisely, you see the rule. So there are 2 levels of abstraction. Now this is a more elaborated example. You can see here nodes, different diseases, and here you can see here are those environmental factors, and they are related to different diseases. And you see these are combinations of factors. So the idea is that system can discover combinations of factors which together influence strongly the presence of a given disease. It also shows you graphically strength of different factors and their influence, and also qualities of influence. For example, sleep. Sleep is a mountain shape, meaning that if you have too little sleep or too much sleep, that's a problem. So we are having those graphical symbols to illustrate qualitative relationships. Now, this result is not claimed to be a new discovery in medicine. We are not saying that. However, we are saying that we have technology that potentially could really make real discoveries in medicine, because this was actually achieved from a relatively small sample of the data. Next step, we'll actually use the whole data set which is available to us, and patterns will be much stronger. And then we may indeed be able to find some patterns that are not known yet to doctors. So you can see there are the rules for each of those diseases. So you can go through the rules and you can actually see more precisely expressed relationships. Now, one thing which I will add to the end, at the end, is that it's very important to specify the Scout's mission. That is, you have to define the knowledge that you're looking for as precisely as you can. The idea is that we launched a Scout that in the other database, it was parent-children survey data. It was looking for a situation in which children start, let's say, taking drugs or not taking drugs. What influences them? Can you predict that? And so on. We found all kinds of patterns. But initially, we just defined Scout very sort of poorly, one may say, and we had 72,000 rules that occupied 30 megabyte disk space, and they ran for 4 days. So this was a huge sort of knowledge base, in quotes, that system created, but it wasn't very useful, too many rules. But then we defined the goal a little bit better by adding more criteria to the Scout definition, and we got already 217 rules for 400 decision classes, so it was quite a lot. Stopped. It's a smart laser pointer. It ends its life at the end of my talk. So application areas, I don't need really to spend much time on this. Obviously, technology of deriving knowledge from data can be applied to very many areas of human activity. What we would like to have maybe the kind of things that you are doing. If we can have input not just from databases as we have now, but maybe natural language form, and system that can analyze the natural language, translate it to forms the system can understand, and then learn from that. And also output in natural language forms. Right now we have some natural language forms, namely those attributional calculus rules that are easy to translate to natural language, but eventually we will have more rich forms. And also more maybe elaborated graphical forms. That's where we're doing research right now. Okay, so this is a list of application areas that we are either already applying or perhaps will be applying this methodology. This research just was founded by National Science Foundation, so I'm very happy to say that we are now supported for the next few years to do this. And we actually have other research support for this research. So I would like to acknowledge publicly that we are very grateful to those agencies. Now, if any of you found my talk a little bit interesting and would like to know more about things I talked so superficially, here is our website, and we have publications there, and you can read those publications. It may take you quite a long time, actually, if you want to read all of them. There's quite a number of those publications, but you can select some of them, and recent ones are downloadable. The other ones, well, if you ask us, we may be able to send you a copy. Now I would like to go to this demo, illustrating natural induction, if you are interested. Loudspeakers, right?
The world of machines has learned and discovered an artificial intelligence exhibit presented by the Machine Learning and Inference Laboratory.
I may mention that this exhibit, the demo, is based on earlier demo that we developed for a Boston Science Museum, and then it went with an exhibit called Age of Intelligent Machines through major museums of science. So we had a lot of people seeing earlier version of that demo, but the earlier version also had other systems, had 5 other systems. This is just one of those systems that learn rules from data. So this demo illustrates my talk. Something not working, but hopefully it will work.
Hi, my name is Q. I am an expert in creating rules for recognizing objects.
All right, let's start with the introduction. The point was, when we designed this demo,
the year is 2120.
It must be very simple to understand.
Your spaceship has landed on a distant planet populated with humans like robots. Your mission is to make a trade agreement between the Earthlings and the robots.
Okay, can you determine a rule that distinguishes friendly robots from unfriendly robots? Some simple rule that you use it. Good. All right, we already have one answer. No more answers? What? Smiling.
A robot is friendly if it is smiling. A robot is unfriendly if it is not smiling.
Okay, let's go for it.
Suppose you meet new robots.
Now you met new robots, and you see that guy on the right is smiling, but it's not friendly. So we have to revise our rule. What's that?
Not smiling interference or something.
Excellent, right.
Invite some of the robots below to join your club.
Yeah, this was too fast, so I can go quickly because you wanted to see that.
Hi, my name is Q. The year is 2121. The robot is friend. Suppose you meet new robot. The robot is friendly if it is smiling and not holding a sword. The robot is unfriendly if it is holding a sword and not smiling.
Okay, so now through this example, you already know what approximately the system can do. Can create rules in natural language from the data that it observes, and data are some simple visual objects. Now let's go to a real part of this demo.
Invite some of the robots below to join your club.
I need someone who will invent and will keep secret some rule for accepting robots to his or her club. You will not tell us the rule, and we'll see whether this program will actually guess your rule. Who wants to? Do you want to try? You can use any rule you can possibly envision or invent, but in terms of features that are easy to detect in those robots.
So we can't pick randomly and see what the rule comes up.
Oh no, we can do randomly. Yeah, that's an easy way to do it. But it's more fun if you can think of some rule and see whether the program will discover your rule or some other rule, maybe equivalent. Want to try? Yeah? Okay, so what we do, we go next. And now you tell me which robot to put to which row. The top row is the row of robots that you accept to your club. The lower row is the row where you will not accept to your club. So you just tell me which robots you will accept. You don't tell me the rule.
How might we describe it?
Oh, as many as you like. You can have just few or the whole row.
Just say first row, third robot.
So, which one?
Pick one guy over.
Which one? This one?
The next one.
Next one?
Yeah, that guy.
You will accept?
Sure.
Good. Sure, fine. Okay, next.
And the guy in the very, very end.
Very end. Okay. You accept. Fine. What about
And guy 2 over 20.
this one?
No, that one. Yeah.
Accept or not?
Yeah.
Okay.
And that's it.
And now you have to give me some which you don't accept. That's too trivial.
Oh, okay. On the bottom row, the second guy, third guy, and the fifth guy.
This one?
Yep.
No. This one? No. This one?
No.
No. More examples?
Yeah, keep going.
Okay. What about this one?
No.
No. What about this one?
Okay.
Okay. Accept. Fine.
No.
No?
Put it on the bottom.
Okay. What about this one?
On the bottom. Everyone else should go on the bottom unless I have it to.
Oh, everyone. I see. Okay. So now, in order to be fair to this program, try to find this solution yourself. How long would it take you? Italian, you recognize, right? But there is also Italian who was not accepted. What?
It's not smiling.
Not smiling, okay, yes. Smiling Italian. Smiling Italian is accepted, good. Yeah. What? Smiling with balloons, but there are some Italians who are not having balloons. So you have to say or type of relation. Okay, which one? This one?
No, because pick all people with smiling faces in the top.
Smiling face. Oh, this one?
Yeah, put them on the bottom. And the guy at the bottom.
And this one?
No, bottom left.
Bottom left. Where?
Yeah.
Here?
Yeah.
Okay, fine. So, are you ready?
Yeah.
You have already some hypothesis? So let's see how long it will take the computer program to find it. Normally it takes about 15 minutes. Do you have 15 minutes? No?
A robot can join the club if its antennas
I was
are
lying, of
not
course.
red, it is holding a balloon or a flag, and its height is medium or tall.
Okay, so that's the rule created. I don't know which rule did you have in mind.
If you had a yellow shirt carrying a flag or a red shirt, and then
All right, so it's somewhat.
I can't even see the color now.
Okay, but we can also. Okay, so this program guarantees that the hypothesis it creates is consistent and complete with regard to all the data. That's a guarantee, but not always the one you should have in mind. But I have also an option. I can say discover an alternative rule.
A robot can join the club if its jacket is red or yellow, it is holding a balloon or a flag, and its height is medium or tall.
I can try more.
A robot can join the club if its antennas are not red, its jacket is red or yellow, and it is holding a balloon or a flag.
So I can try some
A
alternative.
robot can join the club if it is smiling, it is holding a balloon or a flag, and its height is medium or tall.
Okay, so that's closer to some people had in mind. Okay, so we can of course change the data, add or remove example, and try some other. Yes?
So, am I mistaken? It looks like all of the rules that I've satisfied for in CNN
Is what?
are in conjunctive normal form. Does it only have emphasized such rules?
Disjunctive normal form. But you see,
Conjunction or disjunction?
no, it's the disjunction of conjunctions which include internal disjunctions. Because we have concept of internal disjunction of values
Yes,
of an attribute.
Okay.
Okay, so it's a disjunctive normal form of conjunctions with internal disjunctions, right? Not necessary. We have ability also to find exceptions and some other things that come from attributional calculus language. But this example just shows that form. Yeah. But this form is easy to translate to English, as you can see. Well, if you want to try with more classes, for
Is
example.
there any notion of the complexity of the
Yes. Yes, program, if you try, for example, maybe move those examples here, or just we'll do randomly, just for fun to see what happens. Like this. Is anyone who can find a rule now? So there are, in order for the,
A robot can join the club if
complex.
its head is round or square, its body is round or triangular, and the shape of the body and the shape of the head are different, or if its antennas are yellow and its height is tall.
And you see shape of the head, shape of the body and shape of the head are different. You see, just a different concept now of equivalence of two variables. Now, the point is that we, of course, can find alternative rules.
A robot can join the club if
We
its
also
antennas
can-
are yellow or green, and its jacket is yellow or green, or if its antennas are yellow or blue, and it is holding a balloon.
We also can run in a mode that discovers approximate patterns. These are all perfect patterns in the sense that they explain and cover all examples. But you may also have strong patterns, yes?
When comparing equivalent rules, how do you determine which is minimal or a winning scheme?
Oh, depending on LEF. See, LEF has typically such criteria like we want to have minimum number of rules. We would prefer just one. Then we would like to have, let's say, maximum number of examples covered. So one rule should be maximally sort of covering the given facts. Then we may want to have minimum number of elements in the reference. Reference is number of those elements which are linked by internal disjunction. Then we may want to have attributes that are easiest to measure. We have a concept of how easy it is to measure different features. For example, color of the jacket is easy to see, even from a distance. But let's say color of the antenna is harder. So we have different weights for different attributes. Some of them are easier to measure, some of them are harder to measure. So system wants to find also rules that have minimum cost. minimum cost in terms of measuring those attributes. That's why first we try to look whether jacket is a sufficient feature together with something else. And only if you cannot do it, then goes to some more complicated attributes. Yes?
How many robots would you need before you wouldn't find a rule?
I cannot hear.
Within your family of rules, how many robot examples would you need before you wouldn't find a rule?
One or very many. This program can work with one example or with million examples. But
It's the contrary. When you don't find
Just,
a rule,
in other words, enumerating all the robots in the club is also a rule, right?
yeah.
So when is that being the rule?
Okay, let me explain. I think I am now understanding better your question. The point is that this is an inductive inference. Inductive inference is under constraint problem. That is, from the given data, you may generate very many different hypotheses, which are all consistent and all complete with the data. Therefore, you need to have some extra logical criteria to select some hypotheses from many other hypotheses which are all logically equivalent.
You're using some kind of minimum description language.
Yes, Occam's razor, but we do more because, as I said earlier, we have this concept of LEF, and one of the elementary criteria may be minimum description, but another criterion could be minimum cost of measuring attributes. Another criterion may be some relating to some other properties that is desirable. So, system is looking for descriptions that are satisfying the condition for coverage and explanatory properties of the rule, but then are satisfying those extra logical criteria that we impose. So in medicine, for example, we've done experiments with cancer of the pancreas, or distinguishing between cancer of the pancreas and cancer of the liver. Now, we know that if you take a biopsy, that you can distinguish those cancers. But biopsy is not a test that you want to perform if you don't have to. So we first assume that let's see whether the system can try to discover rules that only involve, let's say, blood chemistry tests, which are easier to get. And only if it cannot make good distinctions, then other tests. So you may involve the cost of the attributes also as very important part of your LEF criterion. LEF stands for lexicographical evaluation functional. So it's a multi-criterion evaluation of hypothesis and search for the best hypothesis according to that criterion. You have different application, you change your left, and you get different hypotheses.
I have a very basic question, like how is this related to machine learning?
How is it related to machine learning?
How is this program related to machine learning? Like, I don't see any connection.
Well, depending what you mean by machine learning. Machine learning is a process of creating knowledge from the given data. Knowledge may be in the form of the declarative set of rules like this one, or can be the form of algorithms to perform some function, let's say a robot picking up an object. So this is an example of learning program that given data creates knowledge in the form of rules, and then given more data may create better rules, can improve, can modify those rules given more data, can work with small amount of data, large amount of data. So this is a symbolic learning program that builds hypotheses in the form that are understandable to people. This is one of the things that easy to miss, because people, as you can see in machine learning, and you may be influenced by what you see in the publications today, that a lot of work is being done right now sacrificing the criterion of understandability. They want just some results that they can now apply to given testing data and get high performance, let's say, high accuracy. Like a lot of papers involve decision trees, for example. And they don't look how large decision trees. They never publish, by the way. They don't show you decision trees. They only show you results of applying decision trees to training data. And then they say, 75%, 85%. But you don't see what really program learned. You cannot learn yourself the patterns that have been discovered. And you really don't know, is it good 75% or not? Suppose it's a question of 75% correctness of cutting your leg off. Would you be satisfied with that performance and would agree to have your leg cut off? Probably not. So the performance itself, as it turns out, if you deal with experts or practitioners, is very often not sufficient. Very many people say, I would rather see some pattern generated by machine that teaches me something new about my profession. Let's say finding some pattern relating some symptoms to some diseases, rather than having, let's say, 75.8% accuracy rather than 73. So this idea of generating knowledge in the forms that people can understand for some applications, not all, is extremely important. Therefore, in this work, we've been stressing not only accuracy, which is the dominant pattern or dominant criterion in machine learning today. It wasn't this before, but things change. But we are stressing very much understandability, because we feel that this is very important for many applications, not all, but some.
So I'm trying to understand how I should think about this if I'm an algorithmist.
Yes.
First of all, are you guaranteed to find the minimum cost rule, the minimum cost consistent and complete rule, if any such rule exists?
Well, you know, and I can see that you know, that this is NP-complete problem. So if I have 1,000 attributes, or even 500 attributes, or even 100, I may never find it to guarantee. However, if you are interested in this problem, then I will add one more thing that I didn't mention, that AQ algorithm gives you not only a rule, but also gives you an approximation or estimation of the distance between the rule and the optimal rule. So if that distance comes as 0, then program guarantees finding optimal rule without full search. So there are situations, and this is one of a number of very interesting problems for someone who is interested in the theory of algorithms. This argument has not been yet properly investigated by formal guys who like complexity and working in the theory of algorithms. So it has some approximation. So we were able to prove, like there was a problem that I was very fascinated by this, sort of happy with that. There was a problem in finding minimum representation for 8 variable symmetric function. And in order to do so, I calculated that you have to have about 3,000 years of computation. So I ran AQ with the delta concept, and it suddenly came 0. So I knew that we have actually optimum without doing that 3,000 years of computation. So that argument gives you that estimate, but doesn't give you a guarantee that estimate will be always 0. Therefore, it doesn't always give you optimum.
That's useful. Is there anything else that we could look at if we were comparing this algorithm to another algorithm that tried to do the same thing in terms of runtime, accuracy guarantees?
It's hard to compare because, well, there are two different things. One is algorithm. This is a covering algorithm for solving general covering problem, which can be applied to all kinds of problems, not only learning. It can be used to all kinds of covering problems, first of all, to design switching circuits, to design Boolean expressions, minimum Boolean expressions, and so on. And then there is application of this algorithm to machine learning to learn attributional calculus rules. As you have noticed, attributional calculus rules have greater representation power than, let's say, some other methods like decision tree or conventional rules and so on. So therefore, you cannot compare because, to my knowledge, there's no other method that uses such a rich language. So you will be comparing apples with oranges. But you could clearly invent some other algorithm trying to find attributional calculus rules. Simply, that's an open problem.
What steps do you take to minimize overlearning, especially in the face of...
Pardon me?
What steps do you take to minimize overlearning?
Overlearning? Overfitting?
Overfitting, yes.
Overfitting.
Especially in the case of high noise.
Well, that's a good question, excellent question. What he asked is very relevant in the following sense, that if you have richer language, then you can more easily overfit the data that you have. Do you understand what I mean? If you have, for example, like, let's suppose you want to characterize by some equation some points in a two-dimensional space. And those points are distributed along a straight line, but not exactly straight line. So if you have ability to create high-level polynomials, so you'll be able to fit all this data perfectly. But that may not be really right thing to do because of experimental error, the real relationship is a linear relationship. So that would be overfitting. So the way we of course face that problem as any other learning algorithm, and even more because we have more let's say, expressive representation language. This is why we have LEF. LEF constrains the representation and, let's say, looks for the simplest representation. So if we have a choice between two representations that both have the same explanatory power, then we'll look, let's say, for a simpler representation according to the criteria that we put to left. And then you can change left again and run again and get something else. So this is the way to cope with overfitting. Yes? I don't know, you were first probably, but it doesn't matter. You choose between you.
I have a question about the selection rule.
Between
How do
what?
you select the seed? No, in the API.
Oh, seed you select randomly. No, return. You can select seed randomly, and what we do, because we just don't want to bother. However, you can select seed not randomly. And in those, let's say, applications like to switching theory, designing optimal systems, then we actually chose seed according to certain algorithms. So it depends on the application. You can use some, or for example, you can have learning algorithm. That's what was actually the case in the switching circuit applications. Namely, system runs once and learns somewhat about the function, and then is better prepared to choose better seeds. And then it repeats itself several times. So you can do learning over learning. Yeah. But in this case, we just randomly select a seed. And it doesn't matter. You may think that it matters. It doesn't matter. Even if the seed is an error, is a mistake, is a wrong seed, that means that seed is coming from the positive example set, but by mistake, was put there and really represents negative set. It still will be okay. You know why? Because C, which is wrong, will have poor star. Star generated from that seed will be poor. Will have some poor rule, and that rule will be discarded in the later steps. So it's not so sensitive to which seed you select.
How can you modify your algorithm to get the rows with time sequence?
With time sequence?
Yes.
Right. Well, we've done such a work. We've done not so much with time sequence, but with order, which could be time order, may not be. This is described in several papers, learning to predict sequences. You can find in Machine Learning Book 2 and some other papers on Spark programs. Spark means sequential pattern recognition. Right now we are actually doing that kind of application for user modeling and computer user intrusion detection, where we have sequence of behaviors or interactions with the computer and we modeling that process. We are right now working on it. But earlier work already is described well in publications, so you can see it. Yes, it can be done. The idea is that we are applying different models into which we want to fit the sequence, the temporal sequence. And AQ is used very much for decomposition model. The decomposition model means you look for the part of the sequence and you want to predict, you want to look for the part of the sequence in different cases, many different sequences, and you want to create a general rule that if satisfied, predicts an object non-deterministically. That is, predicts some properties that next object will satisfy. So it doesn't necessarily identify the object, but identifies features. I could show you this, but I just didn't prepare that. So this work has been applied to sequences and can be applied.
My other question is, usually the best rule is a rule with some exceptions.
Yes, IQ 19 and 20 were exceptions, builds exceptions too. So you may say it's called rules with exceptions. And this goes back to my work with Patrick Winston, who you might have heard. I have developed a method to build rules which have exceptions in the situation where exceptions will lead to simpler representations. Yeah, so actually programmers doing that now, right now. Yes. Next, sorry. Yeah, he was first.
So I have a question. One, it seems that it would generate a lot of rules. Do you have any?
What was selected?
When you generate the star, and you generate everything, it seems that the program will take a long time because you will generate lots and lots of rules.
No. Depend. Yes. So what's your question?
And do you have any mechanism to prevent it from happening?
Yes.
And second would be, do you have any principled way in generating LEFs or the user?
LEF.
Yes, or the user has to handle it.
Okay. First question. Indeed, if the problem is complex, let's say you have 100 variables, it may have many different rules in the star. But notice, the number of rules in general may be much, much larger than the number of rules in the star. The star has a constraint, namely must cover the given C. Moreover, rules may be required to have certain properties, and that will constrain further the size of the star. And moreover, what we do, we found out that for machine learning applications, we don't need to build the whole star. We build partial stars. That is, we do the so-called beam search. Are you familiar with beam search? So every star is generated in steps. And in each step, there's a number of partial complexes, that is rules, in this case, generated. And then we trim that set, like beam, to narrow beam. And that beam may just have one complex or one rule. And then we expand again and have another number of choices and then select the best. This is called max star. So max star typically is 1. If you know about decision trees always have max star equivalent 1, because at each step they always select one attribute which is best for the given node. In EQ you have a parameter, max star equals 1 or 2 or 10 or infinite. So therefore you have a beam width, max star is beam width, and it always reduces the number of rules that are currently under observation and under attention to a certain fixed number. And this can be done actually very fast, turns out. So this is how we limit that problem. You are right, it can be many potentially. But it turns out that it's not a big problem. Notice that in machine learning, as opposed to, let's say, combinatorial problems, we really don't necessarily look for somehow mathematically simplest solution. You ask, where does left come from? That's a very good question. You see, one of the issues that were discovered in AI was that setting all kinds of problems as optimization problems where you want to find global optimum is wrong. Because, first of all, finding optimum may be impossible because simply it's combinatorially too difficult. But the point is that even if you found optimum according to your mathematically formulated criterion, that may not be really good because your mathematical criterion may not reflect some of the criteria in real life requests. Suppose your criterion is maximize profit of a company. So you have maximum profit, but you pollute all land around you, and then you lose big because you are taken to court, and then you don't have much profit. So your criterion must be defined in a way that reflects human needs, human users' need, and so on. Therefore, it must come from people somehow. But we are providing simple mechanism. Notice that left is not, if you know that work, it's not a linear, let's say, function, as very often in optimization problems they do. They have a linear function with some coefficients and they don't know where to take those coefficients. Left is defined as a sequence of certain attributes or of the properties and with tolerances. So easier to define, it's easier, closer to our intuition. Yes? Paul, sorry, yes.
The little bit of work I've done in medical diagnosis suggests that the way most doctors reason that a symbolic system isn't really sufficient to express their reasoning, that it's not so much, 3 out of these 7 symptoms, but one symptom is much stronger evidence, one symptom is lesser evidence, that there's some accumulation of evidence that's somehow fractional or probabilistic, and that most of the systems you described, economics or otherwise, have sufficient degrees of uncertainty and complexity that a symbolic solution, while it may be very understandable to a user if you communicate it to them in natural language, probably wouldn't reflect the way the reasoning of a human reasoner actually would need to operate in that domain. Is there any way to address that within this approach?
Yeah, this is excellent, actually, question. It touches upon many research issues. First of all, when you say symbolic may mean many different things. People call decision trees symbolic representations. They are very nice if they are short, but if they have 1,000 nodes, we don't tell anything to a person who looks at a tree with 1,000 nodes. But it turns out that you have also another symbolic representation which has only 1 or 2 rules, which are easy to understand. However, you are right. Rules by themselves, if they are represented just as purely logic rules, yes, no type of descriptions, they are definitely not representing human reasoning, because humans use some logical forms. Of course, we know that we reason in some form of logic, but it's not a formal logic. We do represent some weights behind conditions. We also reason in many different ways. That is, if you are familiar with the work on plausible reasoning, then people would follow different paths of reasoning. And if those paths come, like doctor may try this test and see what happens, and another test or another way of approaching the problem. And then if all those paths come to the same conclusion, then he or she is very confident. If they're going to different conclusions, a doctor would not typically weigh those paths. He may, if he has no other choice, he may want to look for another test, for another measure. People don't like conflicting answers that they have to weigh now and say, this is a little bit better than this. They don't do it, but if they have to, they do it only when they have to. So yes, we have a way to represent this statistical knowledge, probabilistic knowledge. If you notice in those rules which I showed you, each condition was annotated with certain numbers. Well, those numbers are sort of statistical approximations of the significance of that condition. So very much our approach, our, let's say, aspiration is to merge logic with statistics, and that we are very much doing. Our language of attributional calculus is a language that captures logic but also captures some statistical properties of things.
If you interpret the rules LAF,
pardon me?
If you interpret the LAF rule
as
its prior probability or proportional to the negative line of its prior probability or something like that,
right?
Can you regard your method as chain line probability?
Never thought about it. But we would not interpret LF. We would put in the LF, let's say, probability. Probability would one be of the factors to let's say, maximize a posteriori probability.
Yes, that's right.
Yeah, it could be done. So maybe it could be phrased this way.
What you're doing is sampling from the space of rules. That's in proportion to posteriori probability. And if that's the case, that would actually make it quite an attractive method because you can aggregate over the past rules and explain the data.
You can say it sampling, but where sampling implies often that you sort of pick up different things. We are not sampling in this sense. We are synthesizing. We are building a rule from components through reasoning. You know, if you are familiar with my paper of theory of methodology of inductive learning, is anyone who read this paper? I actually produced their rules or suggested rules for inductive reasoning. There are rules for deductive reasoning, which everybody knows. They were established by logicians over hundreds of years. But there are also rules for inductive reasoning, it turns out, especially inductive generalization reasoning. There are falsity preserving rules. And now AQ simply applies some of those rules to data, and applying those rules creates new knowledge, which is generalization of the data, and then evaluates, has many hypotheses, evaluates them according to LEF, selects the best, and then maybe elaborates hypothesis more in view of more data, and again selects the best according to LEF. And LEF can be, of course, modified easily. It's not like fixed like many learning programs. The criterion is fixed. Like decision tree has a gain ratio, let's say. It's fixed, once forever, you just have gain. You have no choice. So our approach is, well, we also fix by default. If you don't want to know anything about algorithms, simply say AQ and data, you will run it, you will get the result too. But if you have a little bit more knowledge about what's going on, then you may define your lab slightly differently according to the problem that you have. So it sort of gives you certain additional flexibility through lab and through other things, through Maxstar and some other things.
Let's stop here. Thank our speaker again.